Welcome to submodule 3 of 3, Key Concepts of Drilling Optimization. In this session, we'll explore how optimization fits into the well design process. In this submodule, our focus is on understanding the sequential steps of well design and how they interconnect. We'll begin by examining the critical role of casing and trajectory design, highlighting how these influence structural integrity and reservoir access. Next, we'll look at survey, fluid, and drill string requirements. These are essential to achieving accurate placement, safe drilling, and efficient wellbore construction. Another important aspect is optimization by design, where we use offset data and reiterations to refine each stage of the process before execution. Finally, we'll distinguish between the factors we can control, such as design choices and operational planning, and those we cannot, such as weather or regulatory constraints. By the end of this session, you should have a holistic view of drilling optimization as a structured, repeatable process that balances engineering, safety, and efficiency. With that foundation set, let's move into the well design process itself. In drilling engineering, the well design process is not a single-step activity, but a structured sequence that integrates multiple engineering disciplines. The first approach to well design always begins with data gathering and validation. Before any casing or trajectory decisions are made, we must collect offset well data, verify its accuracy, and organize it into usable formats. This gives us calibration points and benchmarks that guide the rest of the design process. Once the data are validated, we move into casing design, selecting casing sizes, strengths, and setting depths that can withstand pressures and protect aquifers. The next step is trajectory design, where we map the well path to reach the reservoir efficiently while avoiding collision risks and mechanical limits. After trajectory comes survey planning, ensuring the accuracy of directional control. Drilling fluids are then designed to balance pore pressure and fracture gradients, maintain hole cleaning, and prevent formation damage. Drill string and system design follow, optimizing hydraulics, torque, and drag. Finally, cementing design completes the well architecture by securing zonal isolation. The flow diagram on this slide, placed centrally, shows the sequence from data gathering through to cementing, with a looped arrow reminding us that reiteration is often necessary. With this first pass structure in mind, let's now take a closer look at data gathering and validation. Here, we have a structured workflow we follow for data gathering and validation. It is built around 4 main blocks: collect data, analyze data, provide and integrate solutions, and document optimization guidelines. We start with collect data. At this stage, the objective is to build a complete and reliable data foundation. That begins with reviewing the well design and selecting the most relevant data sets, whether from offset wells, logs, seismic, or daily drilling reports. We don't just gather information, we validate it, checking for inconsistencies, gaps, or errors. Once validated, data is organized systematically and databases are updated. This ensures that the entire drilling team is working from a single, trusted source of information. The second stage is analyze data. Here we focus on learning from the past. Events and limiters from offset wells are reviewed to identify risks such as stuck pipe, lost circulation, or performance bottlenecks. Calibration points are then applied to tune engineering models, ensuring they accurately represent the field reality. Benchmarking is also carried out, comparing our performance against industry or regional standards. From this analysis, realistic performance targets can be set. Moving on, we provide and integrate solutions. This is where the analysis turns into action. We define prevention strategies, mitigation measures, and contingency plans. Forecasting models are applied to predict how the well will perform under different conditions, and these outputs are used to set clear objectives and targets for the campaign. Finally, we document optimization guidelines. This is where all insights are consolidated into practical deliverables, the basis of design, detailed DWOP or drill map reviews, and a specific well program with measurable KPIs. These outputs provide the operational team with clear guidance on how to execute safely and efficiently. Together, these four stages transform raw data into actionable engineering, forming the backbone of well planning and optimization. Next is a short video that shows how technology can help in this process.
By harnessing the power of generative AI, we can transform unstructured legacy data from various sources scattered across your organization into valuable, actionable insights so you can act faster, better, and with more impact. Thousands of your documents contain critical field information. Consider the data contained in all your daily drilling reports. Your field engineers rely on this for a host of essential activities, from analyzing drilling risks to calibrating workflows to optimizing performance and maximizing asset potential. But extracting the information they need is a complex, labor-intensive process that can result in inconsistent, unreliable outcomes, and a lack of contextualization limits the potential of the insights they derive. Our generative AI-powered solution overcomes these complexities. Once a user selects a zone of interest, an engineer can utilize one of our customized domain prompt templates to uncover all relevant information across all available documents, including daily drilling reports. Generative AI will process unstructured documents with domain fine-tuned large language models. This enables a comprehensive overview of the retrieved insights associated with the prompt for the selected region. Our generative AI solution, enriched with domain expertise, transforms unstructured data into precise, actionable insights. It offers unparalleled flexibility to process all document types while significantly accelerating time to value and enhancing decision-making efficiency. See the impact of AI on your business today.
Casing design is one of the most fundamental components of well planning because it defines both the structure and safety of the well. First, we must consider the size range and delivery times available. Logistics often constrain what can be delivered on schedule, so casing selection must align with project timelines. Next, casing must provide structural strength to support the wellhead and withstand environmental loads. It also needs to ensure surface aquifer isolation, preventing contamination of freshwater zones. Pressure containment is a critical design driver. We must ensure that the selected casing can safely manage expected reservoir and formation pressures, while maintaining kick tolerance for unexpected influxes. Metallurgy choices are equally important, especially in corrosive environments such as CO2 or H2S service. We then evaluate mechanical loadings, including bending, wear, burst, collapse, and tensile stresses. Each load case must be analysed with safety factors to ensure casing integrity under both drilling and production conditions. In summary, casing design is a balance of strength, safety, availability, and environmental protection. The decisions made here determine the overall architecture of the well and directly influence subsequent steps like trajectory and cementing. Trajectory design focuses on defining the well path from surface to reservoir with precision and safety. The first priority is collision avoidance at the surface, ensuring that new wells do not intersect existing well bores. This requires accurate survey data and separation factors built into the plan. Next, we must respect dogleg limitations. Excessive dogleg severity can damage drill string components, restrict casing running, or lead to high torque and drag, so we design smooth curvature within tool and casing tolerance. Trajectory planning must also account for formation responses. Some formations may be unstable or reactive when drilled at certain angles, so inclination and azimuth choices are made with rock mechanics in mind. Finally, the well path must ensure correct reservoir orientation and placement. Positioning within the target zone is critical to maximize reservoir exposure and productivity, whether drilling vertical, deviated, or horizontal wells. Survey design underpins directional accuracy and wellbore positioning. We begin with policy considerations, such as whether the redundancy principle will be applied using multiple independent measurements, or whether exemptions are acceptable. Software capabilities also influence survey planning. The next factor is instrument error. No tool is perfect. Each has defined confidence levels and orientation sensitivities. Understanding these limitations helps quantify the positional uncertainty of the wellbore. Survey design itself may be structured in parts. For example, higher density surveys in critical sections such as kickoff points, and wider spacing in less sensitive intervals. During operations, the survey program must be followed rigorously with clear specifications and contingency measures in case of tool failure. Finally, we consider quality control. Survey QA/QC processes are essential to verify that the data meet performance criteria. Errors or poor quality surveys can result in misplacement, potential collision risks, or missed reservoir targets. Drilling fluids play a central role in both safety and performance. The first factor is the environment. Fluids must be compatible with temperature, pressure, and chemical conditions in the well. The fluid density must remain greater than the pore pressure to prevent influx, but less than the fracture pressure to avoid losses. This narrow drilling window often defines the operational margin. Next, we consider rheology, which controls hole cleaning, cuttings transport, and equivalent circulating density, ECD. Proper rheological properties prevent cuttings beds in deviated sections and maintain wellbore stability. Inhibition is equally important when drilling through reactive shales, preventing swelling or disintegration. We also focus on minimizing formation damage. Incorrect fluid chemistry can reduce reservoir permeability and impair productivity. Lubricity is another factor, especially in extended reach wells, where torque and drag can become limiting. Finally, all of these requirements must be balanced against cost, as fluid systems are a major contributor to well expenditure. Drill string design is about ensuring both efficiency and mechanical reliability. Our goal is to maximize efficiency, which means achieving the planned rate of penetration while maintaining stability and control. To do this, we must select the right bit for the formation and the drilling system, whether rotary, steerable, motor, or conventional assembly. The design process then identifies critical components in the string, such as heavyweight drill pipe, stabilizers, and jars, which directly affect torque, drag, and load transfer. Alongside components, we must define critical measurements, including weight on bit, torque, and bending stresses. These values are used to assess mechanical limits. Equally important is the accuracy of measurements provided by downhole tools. If sensor data are unreliable, design assumptions can quickly fail. The final stage is to integrate all these elements into a coherent drill string design, balancing length, stiffness, and hydraulics. Optimization by design means building improvement into the well planning process itself. This is not a one-off activity, but a reiterative process. When a problem arises, we must first have sufficient knowledge to fully understand the cause before attempting solutions. This requires detailed offset data analysis, learning from historical performance and applying those lessons proactively. Reiterations occur at two levels. First, within each element of the process. For example, rechecking casing design if new pore pressure data are revealed. Second, across the entire well design process, where early assumptions may need to be revisited as new information emerges. The central point is that optimization is not a separate step. It is embedded throughout design. Each cycle of data gathering, design, and validation strengthens confidence in the final plan. This iterative mindset reduces uncertainty, lowers operational risk, and increases efficiency. The sequential engineering design process provides the backbone for how we integrate multiple disciplines into a coherent well design. Let's walk through this step by step. We begin with geoscience inputs. This includes stratigraphy, which defines the layering of formations, and geomechanics, which sets the mechanical limits of those rocks. Petrophysical analysis tells us about porosity, permeability, and fluid content, while seismic data gives us structural context and helps identify hazards. Without these foundations, no engineering design can be trusted. With the geological picture in place, we move to trajectory design. Here we define the well path, constrained by target locations, geomechanical boundaries, and the capabilities of both rig and drill string. The trajectory must be technically feasible while delivering the well bore to the reservoir in the most productive orientation. Next are casing seats. These are chosen with sensitivity to geomechanics, placing casing at depths where formations can support the loads and pressures expected. Misplacing casing seats can lead to lost circulation or inability to isolate problematic zones. We then turn to drilling mechanics, fluid design to manage pressure windows and hole cleaning, drill string design for torque and drag control, and hydraulics optimization. This is where modeling tools are most heavily used, helping us forecast risks such as vibration or stuck pipe. Once mechanics are defined, we finalize the casing design itself. Here, we apply burst, collapse, and tensile safety factors, evaluate casing availability, and design floating equipment. Following that is cementing design, where slurry volumes, thickening times, and compressive strength over time are engineered to achieve long-term zonal isolation. Finally, we address other specifications and procedures: rig sizing, solids control equipment, time forecasting, budgeting, contracting, and compliance with API and IADC requirements. The diagram shows all these elements arranged in sequence, but linked by iteration arrows. The interpretation is simple. Well design is a structured engineering workflow, but each element feeds back, requiring constant re-evaluation as new data emerges. This sets the stage for our discussion of the multi-reiterative process. Although the engineering workflow is presented as a sequence, in practice, well design is multi-reiterative. This means we don't simply move from geology to trajectory to casing in a straight line and stop. Instead, as new data becomes available or assumptions are challenged, we often need to revisit earlier steps, refine our inputs, and adjust the design. Take geomechanics as an example. If new pore pressure data are received during offset analysis, this may shift our casing depth selection, requiring changes in mud weight windows, fluid properties, and cementing design. Similarly, if seismic reinterpretation updates the structural framework, the trajectory plan may need to be modified, which in turn affects casing setting depths and even rig capability requirements. These are not isolated adjustments, they create feedback loops. One change cascades across multiple domains, from drilling mechanics to equipment specifications, forcing the team to recheck and optimize the plan. The multi-reiterative process is therefore a safeguard against rigid assumptions, allowing us to design wells that are resilient to uncertainty. The benefits are clear. Multi-reiteration reduces the risk of failure by catching design flaws early. It enhances efficiency by adapting to real data rather than relying solely on predictive models, and it embeds continuous learning, since each iteration improves not only the current design but also the knowledge base for future wells. Drilling optimization is not about designing once, but about designing smarter through repeated structured refinement. Drilling optimization should never be viewed in isolation. A more holistic vision is to design wells that meet not only drilling objectives, but also the needs of completions, workover, production, and surface facilities teams. Each of these groups has different priorities, and their requirements must be considered during the initial design phase. For example, casing and trajectory decisions made in drilling can directly affect the type of completion that can be run. If clearances are too tight, it may limit selective re-entry tools or advanced flow control equipment. Likewise, cementing design influences long-term integrity and may determine how easily a workover can be performed years later. Even drilling fluid choices can affect reservoir performance, potentially damaging productivity or complicating future stimulation. By integrating these downstream considerations into drilling design, we ensure wells are not only drillable, but also serviceable and productive throughout their life cycle. This cross-functional approach reduces long-term costs, improves recovery, and avoids operational conflicts between drilling and production objectives. When we consider optimization at the design stage, there are several factors we can control directly. The first is the type of well being drilled, whether it is vertical, deviated, horizontal, or extended reach. Each brings unique design challenges and requires tailored solutions. Next, we look at service life and objectives. Wells designed for long-term production may need different casing materials and safety margins compared to short-term appraisal or injector wells. Hole diameters also fall within our control. Choosing the correct size impacts casing strings, completion hardware, and ultimately production capacity. Pressure capacities must be defined, ensuring casing and fluids can manage formation and reservoir pressures safely. Similarly, the well inclination at targets dictates how the reservoir is accessed, influencing recovery efficiency. We also control casing to hole clearance, which affects cementing success and completion options. Finally, design choices such as casing versus liner and mud type are within our remit, shaping well integrity and operational performance. Strong engineering discipline in these controllable factors leads to predictable and safe outcomes. With design under control, the next challenge lies in managing construction factors. Once design is complete, optimization continues into well construction. Here, we control a different set of factors. The well location is a primary decision, affecting surface access, environmental impact, and tie-in to infrastructure. Spud and completion deadlines are also within our control. Effective scheduling and planning ensure resources are available when needed, avoiding costly delays. Accurate and timely data requirements are another key factor. Without reliable real-time and offset data, construction decisions can suffer. We also manage contracts and agreement terms, which define responsibilities for drilling services, equipment supply, and performance standards. Alongside this, logistics planning ensures that materials, personnel, and equipment arrive on time and in sequence. The rig and equipment availability is another controllable aspect, where early planning and clear specifications help avoid operational bottlenecks. Finally, we must account for additional services such as wireline, mud logging, or well testing, all of which must be integrated into the construction plan. While subsurface conditions are uncertain, the way we plan and execute construction is very much within our control. Next, we'll turn to the elements that are not controllable. While design and construction offer many controllable variables, we must also acknowledge the limits of our influence. Weather is a prime example. Severe storms, high winds, or extreme temperatures can halt operations, regardless of planning. Regulatory restrictions are another area beyond control. Local laws, environmental rules, and permitting processes dictate what we can and cannot do, often imposing strict boundaries on drilling activity. Similarly, company policies and procedures establish internal rules that may limit design or operational flexibility. These can include corporate standards for safety margins, casing design, or fluid types, which must be followed even if other options appear attractive. Legal requirements also shape our operations. Compliance with contracts, international standards, and liability frameworks is mandatory. Lastly, location itself is not a controllable factor. Whether drilling offshore, onshore, in deep water, or in a desert environment, the conditions of access and infrastructure are largely fixed. While we strive for optimization, external constraints remain ever present. The lesson here is to distinguish clearly between what we can control, what we can influence, and what we must simply manage. With these boundaries understood, we can now review our objectives for the module. As we close this submodule, let's revisit the objectives we set out at the beginning and reflect on how we addressed each one. First, we aim to understand the sequential well-design process. We walked through each stage from data gathering, casing, and trajectory design through fluids, drill string, and cementing, showing how they connect in sequence, but also loop back through iteration. Second, we set out to identify key elements of casing and trajectory design. We examined how casing must balance strength, pressure containment, metallurgy, and environmental isolation, while trajectory design ensures safe, collision-free access to the reservoir within dogleg and formation limits. Third, we focused on survey, fluid, and drill string requirements. We highlighted survey accuracy and QA/QC, fluid design for pressure and stability, and drill string design for efficiency, load management, and reliability. Fourth, we applied the principle of reiterative optimization within well design. We saw how offset analysis, feedback loops, and continuous refinement improve reliability and efficiency across the process. Finally, we distinguished controllable versus uncontrollable factors by separating what we can influence, such as design, scheduling, and logistics, from what we cannot, such as weather, regulation, or location. We strengthen planning and reduce risk. Together, these points capture the essence of drilling optimization as both a structured and adaptive process. This concludes Submodule 3 of 3 on the key concepts of drilling optimization. Please proceed to the quiz to test your understanding of the material we've covered. Thank you for your attention and participation. I look forward to building on these concepts in the next session.